Hey guys, welcome back to another RESK Maths video, and in this video I'm going to be talking about why this binomial expansion formula works. So, obviously I'm sure you guys have come across it, or if you haven't, you've probably come across the other version where it's only talking about integers, positive integers, but this is the more general version, and this is basically an infinite series which allows you to work out an expansion form for this single term or bracket. So yeah, I'm just going to be talking about why this works and trying to sort of prove it, but not really prove it because we're not going to be rigorous or anything. But yeah, so first thing I need to talk about is a Taylor series because that's basically like the entire proof of this formula. So a Taylor series is basically what allows you to map any function. So let's just say we have some kind of weird function like this. Let's just say this. And this is our f of x. So it might be difficult to integrate this. It might be difficult to differentiate this because this could be anything. Like this could be something like I don't know, e to the x, even though that is the easiest function to integrate and differentiate. But, you know, this could be anything, and it's difficult to do certain operations on this. So it would be a lot more useful if we could convert this function into the same thing, but in polynomial form. So if we have this, and we can call this p of x for polynomial, and this is just going to have a bunch of coefficients. So we'll have an a without an x, cx squared plus dx cubed, and so on, like that, just carrying on to infinity. And as we add more terms, we should be able to match this exactly, just like this. So yeah, basically, if you haven't, if you don't know what a Taylor series is, it's basically matching the first point, then we match the derivatives at this point, and then we continue to match like second and third and fourth derivatives to basically mold this polynomial into this f of x function until it's exactly the same. Like basically, if you go to the infinite derivative and they're matched, then they should be exactly the same function because the derivative codes for information about the function's future path, if that makes sense. So yeah, I'm basically going to be expanding this out like a Taylor series, and you should see that it actually matches this over here. So yeah, let's actually start doing that. So the first thing I'm going to do is I'll just define f of x. Let's define f of x to be equal to this function over here, which we want to find this infinite series for, 1 plus x to the n, okay? So our goal is to match this to a polynomial, and you can actually see that this is a polynomial. You see we've got the x squared, x cubed, and then goes on to x to the infinity like this, and all of the n terms are just constants, and these are all just constants. So this is actually in fact a polynomial. But yeah, so we've got f of x and we want to match it to a p of x. So let's write down a p of x, and let's just put this in the most general form. So any polynomial, we'll call it a degree infinite polynomial. I don't even think that exists, but I don't think that's the right term. But anyways, so p of x is going to have a constant term plus b of x plus cx squared plus dx cubed, and so on. You can just see it's going to keep on going until like something x to the infinity, like that. So that is our goal, and we want to match p of x to this general case here. So this is pretty simple so far. Let's rule this off and we'll start matching. So the first thing we want to do is we want to make sure f of x and p of x both go through the same point. At x equals 0. And we're actually going to be using x equals 0 for the entire thing. So we're going to be matching the derivatives at x equals 0. That's actually called a Maclaurin series. It's specific of Taylor series, but that's not too important. Just remember that we're going to be matching them around a point. So if we look back to our example here, it's like matching all the points and derivatives here. So you can see p of x goes through the same point here. You can see if we go to the derivative of that, slopes there, the first derivatives are also the same at x equals 0. So yeah, we're basically just matching it all around x equals 0. And the reason you do that is just because it's a lot easier than matching it around any other point, because the zeros will cancel out. You'll see what I mean. So anyways, let's see what f of 0 actually is. Actually, I will do all the matching in blue, just so it's clear. Oh, blue's not a good color. Let's do red, so it's clear. So f of 0 is going to be 1 plus 0 to the n, which is just going to be 1 to the n, which is just 1, because 1 to the power of anything is 1. Okay, so that's what f of 0 is. And now p of 0, well, you'll see what I mean by the zeros cancelling out. So we have p of x up here, right? Now, what we can do is we can actually just plug in x into all of these, and you'll see, oh, I forgot I wanted to do this in red. And you'll see if we put x equals 0 into all of these, we're going to end up getting all these cancelling out because they've all got a 0 term in them, which is just equal to a. So p of 0 is just equal to a. And remember what we said about matching. So we want to make sure that f of 0 is equal to p of 0. So therefore, if we match both of these, we can see that a is going to be 1, just like that. So that's our first term. We've got a in our polynomial. And now we're going to do the same thing, but for the first derivative. So make sure first derivative is the same. So now let's do the same process. First of all, we've got to find derivative of f. And this is pretty simple. If we look back at f, when we take derivative, we're just going to move this down here. And remember the chain rule. So we've got to multiply it by the derivative of the inside function. But since the derivative of this is just 1, just multiply by 1. So there's nothing over there. So we can actually just say that the derivative of f of x is just going to be n multiplied by 1 plus x to the n minus 1. Because remember, we have to subtract 1 from this. And that's going to now let us work out what f of 0 is. So f dash of 0, that's just going to be n multiplied by 1 plus 0 to the n minus 1. And again, remember that this is just going to be 1. So 1 to the power of anything is just going to be 1. So this is just n. And let's go on the page. And let's do the same process for p of x, p dash of x. So the polynomial we want to differentiate. So we've defined it up here. Now if we differentiate this a term is going to cancel out because it's just going to be a constant, and it's going to become b. So I'll just write the whole thing out. Let's just put this in a different color. D by dx of a plus bx plus cx squared plus dx cubed, just like this. And that is going to come out to become, now I'm just going to leave the coefficients as they are because it'll make sense later. So we've got 1 times b plus, move the 2 down there, 2 times x, no, 2 times cx, and then we've got 3 times dx squared, just like that. And now finally we can evaluate this at 0, and this is going to give us, well, when we plug 0 into all of this, you can see this is going to go 0, this is going to go to 0. So the only thing we're going to have left is this 1b term. So we can say p dash of 0 is going to be b. It's going to be b. And remember that we want to match them. So we want f dash of 0 to be equal to p dash of 0. So therefore, b is equal to n. Nice and easy, just like that. So there's that. Now we've got these. So let's do the exact same process for the second and third derivatives. So second derivative match. And I'll just do this a bit quicker, just so we're not spending as much time on doing the same thing. But obviously take double derivative of f dash, and that's just going to be, again, move this down there. So n minus 1, n 1 plus x to the n minus 2, and evaluate that as 0. You're going to get, well, this is going to go to 1, so this entire thing is going to become 1, which is just going to leave n minus 1 times n. And let's do the same process for p double dash. So p double dash of x is going to be d by dx of p dash, which we figured out up here was just 1. Okay, we'll just leave the coefficients in. 1 plus 2cx plus 3 dx squared. And differentiating that, you're going to get, well, this is just a constant, so that disappears. And moving the 1 up here, so you're going to get 1 times 2c plus, move the 2 down there, and plus 2 times 3, like so. Okay, and now, so I just realized that this dx might be a bit confusing, but this d is just a constant, so I'm not referring to dx like in dy by dx. I'm just talking about d as its own constant. So, yep, and now let us match these. So if we put 0 into all of this, that's going to go to 0. The entire term is going to cancel out. So all we're left with is 1 times 2 of c. So therefore, this is the answer. So when we match both of these, we're going to get n minus 1, n is equal to 1 times 2 times c. So that lets us know that c is equal to n minus 1 times n over 1 times 2, like so. Okay, and I guess I'll just do it for the final one, the third derivative, which we're going to match, just so we can start to see the pattern a bit more. So third derivative match. And yeah, the reason I'm doing this for all three of them is that we should be able to see a pattern. So let me just put, I'm just going to, actually I'll do that at the end. Yep. Okay, so let's find the triple derivative of f. Pretty simple again, because this is not going to really use the chain rule at all. So we've got n minus 2, n minus 1, n, and once you do that, you've got to take away 1 as well. So you got 1 plus x, n minus 3. Evaluate this at 0. Just going to put this in here so you can see this goes to 0 again. Just goes to 1, so this entire time does nothing. So evaluated at 0, this gives us n minus 2, n minus 1, and n. Same kind of thing for p triple dash of x. We want to work out the derivative of this, which is derivative of the previous thing. So let's write in all these brackets again. And I just realized I should probably be continuing this on, because this is an infinite series. It's just that all the terms are going to get cancelled out by 0. So yeah, we'll just put in these numbers like so. And just so it's nice and clear that this is p of x is actually an infinite series, but I'm just not showing all the terms because I don't have an infinite amount of time. So yeah, d of x, and taking this derivative, we are going to get, this is going to cancel out, d of x comes down here, so we're going to get 1 times 2 times 3 times just d. And of course, that continues on infinitely. So yeah, now when we evaluate this for the final time at x equals 0, you can see all these other terms, they'll have x to the 5, I mean not x to the 5 anymore, but you know, they'll be in this kind of thing, so they'll all go to 0, which means the only term which is going to have some kind of value is the dx term, sorry, just the d term. So when we put this in, f triple dash of 0 is just going to give us 1 times 2 times 3d. So for the final time, let's match up f triple dash of 0 and p triple dash of 0, which is going to tell us that, well, n minus 2, n minus 1, and n is equal to 1 times 2 times 3d. So therefore, d is equal to n minus 2, n minus 1, n over 1 times 2 times 3. So hopefully you can start to see the pattern now. If I just go back and let's substitute all this stuff back in. So we've got our d term, we've got our c term up here, we've got our b term, and we've also got our a term, which I've already circled. Let me just do it in green, boxed. So let's remind ourselves what these terms actually are. These are the terms to the polynomial series, which is trying to match the f of x series, just f of x function, which was 1 plus x to the n. And this is matching it, so we had a plus bx plus cx squared plus dx cubed, which went on forever. And we've just worked out these a, b, c, and d terms, so now we can put them back in. We know that a is just 1, so 1 plus b, which is n, nx, plus c, which is n minus 1, n over 1 times 2, plus d, it's actually cx squared, so let's just add the x squared in, and then plus d, which is n minus 2, n minus 1 times n, all over 1 times 2 times 3x cubed, like so, and that continues on forever. If you just carry on expanding them out like I have, then you'll get this. So yeah, you should see here that now you should see why I've actually included all of these terms and not just simplified them, because I hope it's clear that we can actually just simplify this to 1 plus nx plus n minus 1 n over 2 factorial. That's the important thing, because if you imagine, as we take more derivatives, if this was like 5, it'd keep coming down, keep coming down, keep coming down, just like that until it's eventually at 0, and then it gets cancelled out, which is why it's just a factorial, because we're just multiplying descending derivatives like that. So yeah, you can see this is how we've managed to get this pattern, but there's still a bit more to prove. Well, not prove, but, you know, explain. So this is our p of x term, and if we go back to the start, you can see we've managed to prove why this is the formula. But one thing you also probably know is that the x here needs to be lower than 3, so actually lower than 1. So actually the modulus of x needs to be, I think it can be lower than, I'm not sure if it's lower than or equal to, let's think about this. Yeah, it has to be lower. It cannot be lower than or equal to. And let me explain why. Okay. So, as you can see, these x squared terms, they keep going up until you get to x to infinity. So, if we imagine this modulus of x, if it was greater than 1, then what would happen is this x to infinity term would also be greater than 1, because let's just say, like, if you have a number greater than 1, you're going to have 5 to infinity is obviously infinity, right? But if you have a number less than 1, like 0.5 to infinity, every time you multiply it, it actually gets smaller. So when you take it to infinity, it's going to go to 0. And that's why we need to make sure this is less than 1 to ensure it converges on the right answer, on a fixed value rather than just divergent and giving us infinity. So that's why it always comes with this condition that the modulus of x has to be less than 1. But yeah, now that we've proved that, I hope it's pretty clear why this works. So we've mapped this f of x function onto our polynomial representation over here. And that basically allows us to expand out anything. One thing that you should be aware of, though, is that this isn't really a real proof, because I've used the derivative power rule, like it's basically the underlying mechanism for this proof, not proof. But the thing is, I think the derivative power rule might be proved using binomial expansion, which this is basically. So that's why it might be a bit difficult, and it might be a circular proof, which is why I don't think you can really prove this rigorously using this method. There's just one more thing. So you might be wondering what to do if, let's just bring it down, if f of x is, actually I'll just put it on a new line. Yeah, so you might be wondering what to do if f of x hasn't got the 1 in front. So what if it's like 5 plus 1/5? No, that's a bit confusing. 5 plus 1/3 x to the n. So it's quite simple, actually. All we have to do is we got to factor out this 5. So put this all in brackets, and we can just factor out the 5. And then what we can do is we can just expand it out normally like so, because then we can just put 5 to the n multiplied by 1 plus 1/15 x, like so. And then we can use our expansion over here for this, just put in, instead of x, just put 1/15 x, if that makes sense. And you can just work out 5 to the n using a calculator. It's just going to be like a constant. So yeah, that's how you solve for those kind of situations. But yeah, thanks for watching, and that was how you explain this binomial expansion into this infinite series using Taylor series. So thanks for watching, and I'll see you guys in a future maths video. See you guys later. Bye.